Very happy to be here, at least virtually. And I'm realizing that I think I last went to a talk at the Royal Institution in 1975 when I was 15 years old, 45 years ago. And the fact that I remember that talk, it was about liquid crystals, is probably a good sign. But one of the things that I was thinking about is what has changed in the world in the last 45 years. And I think at sort of an intellectual level, the single most important change that we've seen has been kind of the rise of computation, both as a practical, technological kind of thing and as an intellectual kind of thing and a way of thinking about the world. And I've been fortunate enough to be involved in a bunch of things that have happened both on the technology side and on the intellectual side in sort of the rise of computation. One of the things that I had long been thinking about is, could this kind of computational paradigm that we've been building be helpful in understanding sort of a pinnacle problem of science, kind of how the universe is fundamentally constructed, what the fundamental theory of physics is. And I'm very excited that over the last year, we've made just spectacular progress in that. Progress I didn't think was necessarily going to happen for 100 years. I mean, we've been greatly helped by the fact that 20th century physics was so successful, with general theory of relativity giving us ideas about gravitation, quantum field theory giving us ideas about particle physics and so on, leveraging those two approaches and now injecting this computational paradigm, we've managed to make, I think, spectacular progress. And I'm actually very confident that when it comes to sort of finding the fundamental theory of physics, if we think of that as sort of climbing perhaps one of the tallest mountains of science, we haven't got to the top of the mountain yet, but I'm pretty sure we're on the right mountain now. And it's pretty exciting to kind of see the view from where we are so far. And I want to talk about that a bunch today, but I thought I would start off by talking a little bit about this idea of computation. And maybe I can tell you a little bit of my personal history and sort of how I've come to be involved in these kinds of things. Back when I was listening to that talk at the Royal Institution back in 1975, I was in America, a high school kid at school in England, and I had gotten very interested in physics. I guess I probably was right around the time I was had discovered that yes, a kid could do research too, and was starting to do things like publish papers about physics and so on. But there was this one thing really sort of holding me back from doing physics, which was there was all this, as it seemed to me, very mechanical, mathematical calculation to be done, which I wasn't particularly good at and which I didn't find very interesting. But I just about discovered at that time these things called computers that I thought could be made to do a lot of those sort of calculational things that I didn't want to do in physics. So I kind of got started using computers as a tool at first to do physics, and sort of quickly evolved to the point where that was a key part of being able to make progress in physics. But then a few years later, I sort of became a physicist. I was involved in particle physics and cosmology and things in the late 1970s, which was a kind of a golden age and those kinds of things. So it's kind of fun that things one did when one was a teenager sort of still people care about today, because one happened to do them at a time when a field was in sort of rapid growth. But I got much more deeply involved in understanding how one could do things computationally and understanding what sort of the foundations of computation were. And I then started thinking about, okay, I'm trying to make progress in understanding how the world works and how nature works and so on. And I got thinking about how do I make models of all of these complex phenomena that we see in nature, whether it's biological phenomena, whether it's complex fluid flows, whether it's all these kinds of things. And so my first instinct was, well, I'll go back to those sort of mathematical physics methods that I learnt from doing things like particle physics and so on. But it turns out those didn't work very well in kind of understanding how to model these more complex phenomena in nature. And so I sort of started thinking, okay, we've got this idea of making models of things, having formal models where we can write down some kind of abstract system and say this is going to be a representation of how the world works. What kind of abstract system can we use to represent how the world works? Well, we have been using for the last 300 years mathematical equations. That was the kind of Galileo Newton sort of idea, was let's roll in mathematics and in particular calculus as a way to describe the world. Let's write down differential equations that describe, you know, the motion of the Earth around the sun or whatever else it is. But so I got to thinking, okay, can we generalize this idea of making abstract models of things to go beyond the specifics of mathematical equations? And at the time, this sort of paradigm of computation was something that I knew something about. And I kind of started thinking, well, what if we use more general rules for things, rules that can be represented as, let's say, simple programs, rather than rules that can necessarily be represented as mathematical equations? So that kind of got me into the question, sort of a basic science question of, okay, if the world is described by programs, what might those programs be like? And in particular, we don't imagine perhaps that the world might be described by programs that are these big, long, complicated programs of the kind that we write for practical purposes, so to speak, in doing the work that we do. They might be just programs picked at random, maybe very simple programs picked at random. They might be the things that are sort of running nature. So then the question comes up, well, okay, what do those simple programs actually do? So that was something that one could try and do sort of analysis and try and think about it. But it's also easy to just do an experiment. In this case, it's not a physical experiment of the kind that the Royal Institution is famous for. It's more, it's a computer experiment. It's much easier for somebody like me to actually get to work. So let me show you a computer experiment that I did first in the 1980s, early 1980s. But although it took me a while longer to realize kind of its significance. So I was interested in looking at the very simplest possible programs. And these programs, they're things that get called cellular automata. And they just have a line of black and white cells. So just a line of cells, each one is black or white. And then there's a particular rule. Let me, I can do this live here. Let's just make one of these. Let's say this one. Okay, so this is a rule for one of these cellular automata. So line of black and white cells, and this rule is saying if you see a particular place in that line where there's a white cell and a black cell on its right and a white cell to its left, then make that cell in the middle black on the next step. Okay, so a very simple rule, just says what to do in each of those 8 cases. Okay, so let's try running this and let's actually see what it does. So let's go ahead and do that. So let's just start it off from, let's say, one black cell at the top. Let's just make a mesh there just so it's easier to see. Okay, here we go. So this is, actually, let me just maximize this window. So this is what happens according to this particular rule. We start off with, let's pick this cell here. So it's white, white, black. And we go and look at the rule here and it says white, white, black, and that should make black on the next step, and that's what happens here. So very simple rule, started off from one black cell, very simple behavior that we get out. Kind of might say, okay, it's kind of what we'd expect. Put in a simple rule, we get it, it does something very simple. Okay, let's try a different rule. Let's say this rule here, let's try running that. Okay, a little bit more complicated. We've changed one bit in the rule here, and we've got out, instead of just this uniform black pattern, we've got out this checkerboard. Okay, let's try a different rule here. Let's change a few more bits here. And let's try this rule here. Okay, now it's doing something a little bit more complicated. So again, this very simple rule, this is what it does. So let's try running this more steps. Let's say 300 steps. Let's get rid of the mesh so we can actually see the thing. Okay, so what that did was it had this very simple rule, yet it made this very intricate pattern. But it's a very recognizable pattern. It's a nested fractal pattern. And we might say, okay, well, if the rule is simple, then even if the pattern may not be uniform, for example, there must still be some very easy to recognize regularity to the pattern. Okay, well, now you can ask the question, let's look at all possible rules of this kind. Let's just go, in a sense, we can think of there being sort of a computational universe of possible programs out there, and we get to kind of turn our telescope to this computational universe and kind of see what's out there. So there are 256 possible programs of this type. Let's just go ahead and just write a little program that just asks to show us a picture of what every one of those programs does. Okay, so let's do this. Let's say, okay, so we're just going to say this. Did I get that right? Okay, so let's say 0 to 255. Okay, so this is now going to work out for every possible rule of this type what happens. So we're starting off from one black cell here, and we're seeing what it does. So some of the time, what it does is really quite simple. There's a black cell. It just kind of runs off to the left there. In these ones, it's alternating black and white. It's doing pretty simple things. We keep going. We keep going. We're kind of looking out into this computational universe of possibilities. Okay, we see a nested pattern there. Okay, that's kind of cool. Let's keep going. Let's keep going. Okay, this is my all-time favorite science discovery. So this is, if we count these rules off, we can number them. This is rule 30. That comes from just the binary decomposition of the number 30, represents the pattern of bits that corresponds to this program. Okay, there's rule 30. So this, let's take a look at what happens with rule 30. Okay, so let's go back up here. Let's say what is the rule for rule 30? Okay, here's the rule. It's another one of these very simple things. Let's try running this rule and let's see what it does. Okay, this is what it does. Isn't that incredibly weird? We started off from just one black cell at the top. Maybe I can show it in a little bit, little fewer steps, just so you can see what's happening here. That's just 50 steps. We started off from one black cell at the top, and we're just following the simple rule over and over again. And look at how complicated the result is. And here, I'll run it for 500 steps just to see what happens. You might say, oh, if you run it long enough, it's going to resolve, and something simple, it will be obvious that it came from something simple. Well, yes, there's a certain amount of regularity that you can see over on the left there, but most of this pattern just looks really complicated, really kind of random. Actually, if you look at the center column of cells here, it is for all practical purposes random. In fact, we've used it in Wolfram Language. We've used it as our source of pseudo-randomness 30 years now. And it's kind of a little bit, what's going on here? How do we understand what's going on? It's a little bit like the digits of pi. You know, there's a procedure for generating the digits of pi. It's the ratio of the circumference to diameter of a circle. But once you generate the digits, 3.14159, et cetera, et cetera, et cetera, that sequence of digits, once generated, seems to us completely random. And it's the same kind of thing going on here. We've got a definite rule for generating this pattern, but once generated, the pattern seems to us in many ways completely random. What we didn't know, though, was that out in this computational universe of possible programs, this is such a common thing to see happen. It's really common to have a situation where, even though the rule is very simple, the behavior that you get is incredibly complicated. It's kind of a sort of a shocking discovery that, in a sense, you might have thought that if you want to make something complicated, if you just discovered something in the natural world that looked like this, you'd say, gosh, that must have a complicated origin. But no, that intuition is wrong. That intuition is what we get from our traditional experience with engineering and so on. You know, if we want to make something really complicated, we have to go to lots of effort. We have to, put in lots of engineering effort to make it. But what this is saying is, no, in the computational universe, that's not how things work. You can have this very simple rule, yet you can get this incredibly complicated behavior. And I think this is a really incredibly important fundamental fact. And actually, over the last 35 years or so, it's been sort of emerging that this fact affects just all kinds of different things and kind of explains a lot of mysteries that we've had in science. I think probably the biggest sort of meta mystery is when we look out at nature, nature seems to be making all of these complex forms, all these complex kinds of things. How does it do it? What is the secret that nature has that we as humans and in our engineering and so on haven't tended to have? Well, the secret is that out in the computational universe, even very simple programs can show very complicated behavior. That's just a sort of fundamental abstract fact that nature happens to make use of when it produces complex things out there. But when we do engineering, we don't tend to do this because our tradition of engineering has been, we're building an engineering system. We want to foresee what we're going to build a system to do this particular thing. We want to set it up so that we can foresee exactly what's going to happen. So we don't want something where we just have a simple rule and it does all this complicated stuff. We want something where we can readily predict from the setup of our system exactly what it's going to do. At least that's often what we want. Now, in fact, when we kind of, as we look at different kinds of sort of approaches to engineering, that is changing somewhat. But let me talk a little bit about the sort of the bigger intellectual picture around what's happening in a case like this. It all, I think, relates to this thing that I call the principle of computational equivalence, which is sort of a very general principle that lets one understand a lot of what goes on in the computational universe. So let me kind of tell a little bit of a story here. I mean, when we think of what is this system doing, we can think it's doing a computation. It's starting from its initial configuration of ones and zeros, blacks and whites, whatever, and it's running this rule and computing what it does. And we can think of this as doing some kind of computation. Question is kind of how sophisticated a computation is it doing? Is it the case that when the rule is sufficiently simple, the computation must also be correspondingly simple or not? Well, what this principle of computational equivalence says is if you look in the computational universe at all possible programs and so on, then as soon as the behavior you see isn't in some sense obviously simple, the computation that it corresponds to is as sophisticated as any computation that gets done. So it's a surprising thing. You might think that when you have a program and you progressively make the program more sophisticated, that the computations that program would be able to do, the computations that system, that machine, whatever you want to think of it as, would be able to do, would also get correspondingly more complicated. But it isn't the case. Instead, what this principle of computational equivalence tells us is that as soon as we get past a very low threshold, boom, everything has sort of the maximum level of computational sophistication. So this idea has many consequences. One of them is something we've known for a long time, which has already had a very important technological consequence for us. It's the idea of universal computation. I mean, if we went back a little bit more than 100 years and we said, how do you compute stuff? You've got these mechanical calculators. You can buy an adding machine. You can buy something that takes square roots. You can buy a machine that does this or does that. One might have thought that every different kind of computation one wanted to do, one would sort of have to buy a different machine to be able to do that computation. But the thing that emerged mostly in 1936 with Alan Turing's work, but actually there was a precursor that is about to have its centenary, invention of some things called combinators, which were not well understood at the time, but which are actually sort of a precursor to this idea. But what emerged most clearly in the work of Alan Turing in 1936 was this notion of universal computation. So the idea is you can have a sort of a single machine which, by giving it the appropriate initial conditions, by setting it up initially in the right way, you can get it to do any computation you want. So in other words, instead of needing to go buy a new physical piece of computer to do each different kind of computation, you can just stick with one computer and just feed it a different program and have it do different computations. And that idea has obviously been sort of a critical idea for technology because it's the idea that makes software possible, and it's the idea that's led to basically a large fraction of modern technology. This idea of universal computation, the idea that you can have a fixed computer that can run all these different kinds of programs. Well, one of the things that this principle of computational equivalence says is that there's sort of a question of how much effort do you have to go to make a universal computer? How difficult is it to make a universal computer? And you might think, based on our actual experience with computers, it must be really hard. You know, you have to build this microprocessor. Maybe it has 100 million transistors, 1 billion transistors in it. There's lots of detail to make this thing that can be a universal computer. But what this principle of computational equivalence says is, no, that's not the case. Pretty much in the computational universe, anything that isn't doing obviously simple things is going to be able to do universal computation. And that includes things like this Rule 30 cellular automaton. We don't absolutely know for certain that Rule 30 does universal computation, although it seems extremely likely. In this particular case, Rule 110, I can show you that one. It happens to grow only on one side here. So let me show you. Okay, that's what it does. Let me just show it for a little bit longer. This particular rule we know is capable of doing universal computation. And let me make that a little bit plausible here, because we can say let's start it off with a random initial condition. Let's just take 2,000 random cells there. Okay, well, that's a little bit high resolution. Let me go down here. Let me make okay. There it is, just starting with random initial conditions. So it's like a random program. And what you see is all these little structures. You can kind of imagine that these are like, bits, ones and zeros, kind of going around in wires in a computer, and they're sort of interacting with each other, and they're doing logic operations and so on. And with lots of effort, one can show that, yes, in fact, one can set this up so that it can actually do universal computation. And so this is kind of a piece of evidence for this principle of computational equivalence, is that yes, even among these very simplest possible cellular automata, there's already one that we know is capable of doing universal computation. Actually, a number of years ago now, I had wondered about the very thing that Alan Turing had worked on, Turing machines. I wondered what was the very simplest possible universal Turing machine. And it turns out I had kind of guessed that this particular one, which is the first Turing machine, that's sort of a representation of the rule for the Turing machine, the first one that was not doing obviously simple things. And I put up this prize, and this young English chap, Alex Smith, in a limited number of months actually, was successful in proving that yes, in fact, this particular Turing machine is universal. It is capable of being programmed to do anything you want. And that's another sort of piece of evidence for this principle of computational equivalence. Well, so what are the consequences of this principle of computational equivalence? One of them is universal computation is easy to find. You can kind of make almost anything be a computer if you know how to program it. And that means that you can, so let's go back then to something like our Rule 30 and ask what sort of the significance of knowing that it is a computer, knowing that it can sort of do an arbitrary computation, what the significance of that is. So one question is, how do we predict what Rule 30 is going to do? Well, one thing we can do is just run it and see what happens. This was 500 steps. We can run it for 500 steps and kind of see what it does. But we might say what science is supposed to tell us is how to make predictions, how to jump ahead and not just have to run every step, but how to say, we know what the answer is going to be. We don't have to run every step. And in a sense, in the tradition of mathematical science, that's been something that we've routinely been able to do. You know, if we want to find out where will the Earth be 1 million years from now, we don't have to trace the actual motion of the Earth for 1 million years. We can just plug a number into a formula, at least in the idealized two-body problem, and say this is where the Earth is going to be. We don't have to just follow through each of those steps. So that notion of sort of computational reduction, of being able to be smarter than the system itself and say, yes, I know the answer, I know what it's going to do after a long period of time, that's the tradition that we've been used to from kind of mathematical sciences. What we learn from the computational universe is that we don't get to do that. The principle of computational equivalence says you can't do that. Because in a sense, what happens is if we're going to predict what this is going to do, we're having to say we as the predictors somehow have to be smarter than the system itself. The system itself takes 500 steps to do it, but we can jump ahead and we can do it in 2 steps. Well, the principle of computational equivalence says that's not going to work because in fact, both this system and our brains or our computers or our mathematics or whatever, they're all equivalent in the level of sophistication of computations that they can do. And so in a sense, that forces there to be a sort of computational irreducibility to the behavior of the system. If the system takes some amount of computation to do what it does, then our brains will have to do a comparable amount of computation to figure out what the system is going to do. So that's in a sense why this system looks to us complex, is because in a sense, we don't get to be able to predict. We don't get to be able to jump ahead and say what it's going to do. This has all kinds of consequences if one's interested in things like the philosophy of free will and so on, and understanding, you know, what is predictable and what is not, and so on. But it has lots of kinds of consequences like that. If you want to ask a question like, what will the system do in the end? Well, let's take an example from Rule 110. Let's ask the question, if we run this for a bunch of steps, we can say, what will this do? We got all these little structures that are running around here. Will these structures survive or will they eventually die out? How will we figure that out? Well, this is a computationally irreducible system. So really, we're stuck with just saying, well, let's go tracing more and more and more steps to see what's going to happen. Well, we don't know how many steps it's going to take to resolve what's going to happen. And so this is a problem where if we say, well, what's going to happen in the end after an infinite number of steps? Well, it could take us an infinite amount of computation to figure that out. So we have to say that that question is something that is formally undecidable. And actually, this is the same exact story as Gödel's theorem in mathematics. This is a kind of concrete version of the effect of Gödel's theorem and the idea of undecidability. This particular case, I think, if I remember right, that by 3,000 steps, maybe, we might have resolved this particular case. Let's take a look. Yes, I think so. After 3,000 steps, we see, well, this particular pattern, nothing, it eventually dies out. But we couldn't have known how many steps we would have to go for to make the thing die out. So, okay, let's, you know, knowing that this computational universe has many sort of rich capabilities. What does that do for us? Well, it gives us a great source of models for things. It also gives us a great source of things for technology. I mean, in terms of modeling things, one of the things that's really kind of silently happened over probably the last 20 years, and I made this big book called The New Kind of Science, which was basically about doing science by thinking about things in terms of the computational universe. And I don't know whether it's causation or correlation, but in the years since that book came out, there's been really a big shift in the way that people have made models of things from a situation that had been going on for 300 years, where people made models of things going to equations and so on to make those models, to a situation where people, when they make new models of things, almost always do them using programs, not using mathematical equations. So that's been a sort of an important consequence of this kind of a way that the computational paradigm enters into science. And once you are making models in terms of programs, you get to see phenomena like computational irreducibility all the time, and you get to realize how important simulation is in figuring out what's going to happen in systems and so on. But another consequence is in technology. What, in a sense, we're doing when we look at when we look out into the computational universe, we're seeing this kind of inexhaustible supply of interesting ideas about things that can happen. Interesting algorithms that do different kinds of things. I don't know, let's run a different random cellular automaton. This is rule 73. Okay, it does something different. We can do like all these different rules. They're useful for different things. In a sense, we're able to take what's out there in the computational universe and mine it for different purposes. Of these 256, what I call elementary cellular automaton rules, it's been really remarkable over the last 40 years how many of them have found uses. I like rule 184, which I always thought was kind of a boring rule, turns out to be the standard minimal model for road traffic flow these days. And kind of each one of these rules has a certain is a different kind of program. Okay, this is the minimal model for road traffic flow. These are kind of cars flowing freely. These are traffic jams starting up. But in any case, this is in addition to sort of mining these programs for models like for road traffic flow, we can also mine them for things that are of technological use. Like, for example, I mentioned that Rule 30 is a good source of random numbers. It's also a good way of making certain kinds of cryptography systems. So in a sense, we're going out into this computational universe, and we're finding things that we can consider useful for our technological purposes. Now, in a sense, this is something we've been doing forever with physics. We're saying, go out into the world. We notice there are magnetic materials. We notice there are, for example, liquid crystals. And we realize that, yes, we can find a use for liquid crystals. We can make them into displays or whatever. We can, there's a thing in nature which we can use in a certain way. And so it is with the computational universe. There are these things that just exist out there in the computational universe. And some of those things we can kind of capture and mine for our technological purposes. And so there's kind of a way of thinking about sort of our relationship to the computational universe is more or less this. There are things that we humans want to do. There are goals we have, there are things we think about, and so on. And then there's this sort of ocean of computational capability out there in the computational universe. And the question is, how do we get to find the things that are useful for our particular goals? You might look at one of these cellular automata and say, well, that's wonderful. It makes an interesting picture, but I don't know what it's useful for. Maybe it's useful for making art or architecture or something. Maybe it's useful for doing image processing. But when we have a goal, then we can go and kind of go out into the computational universe and see whether we can find a computational system that can satisfy this goal. So one of the things, and I don't want to segue too far into this, but one of the things that I've spent a large fraction of my life trying to do is to build a bridge between kind of what we humans want to do and what the computational universe makes possible. And kind of the main focus of that has been building a computational language that allows us to kind of express things computationally. So, we're interested. I've been using Wolfram Language here to do the things I've been doing here, but, you can, I don't know what I could, I could just pick up. I could do some random thing. Let's say I'll make some random graph, or I could say, take that random graph and show me, what are the communities that exist in this graph, let's say, or I could say something. I could do all kinds of other computation, and kind of the notion is, can we sort of can we set it up so that when we want to think about something in the world, we have a language in which to think computationally, and then a language in which that computational thinking that we do can be translated into something that can actually be executed computationally from this kind of computational universe of possibilities. And one of the big things that's been important there is actually getting kind of knowledge of the world to be part of the computational language that we have, to be able to express things where we can say, I don't know, let's try something like this. Let's say capital cities in Europe. I can enter this in natural language. Our technology powers the knowledge systems and things like Siri and Alexa and so on. And that's making use of this kind of idea of being able to take natural language and turn it into some kind of precise computational language that a computer can understand. So there are, capital cities in Europe, and I could say something like, I don't know, let's just say, let's take those which are now sort of computationally represented things and say, let me make a picture of where those are, or maybe I could do something more ambitious. I could say, let's try taking those, and let's say something like, find shortest tour. So we can do that. Okay, there we go. And then let's say, that's the best way to do this. I can just take that and say that. Okay, so now I've got those cities in that order. And then let me say, and I should put all this together so you can see it together. But the basic point is that we should be able to sort of express this idea that we want to find sort of the shortest tour between capital cities in Europe. We can express that in this computational language, and both we as humans can understand it, and the computer can understand it, and then execute it for us. This is a really powerful thing. I kind of, my view of what we're achieving with this is something like the following. Back, it's now 400 years ago, there was kind of, people were thinking about doing mathematics. And when they talked about doing mathematics, they usually talked about it in terms of words. They would describe mathematical operations in words. But then people started inventing mathematical notation, things like plus signs and equal signs and so on. And then kind of this mathematics idea really took off, and one started having algebra and later calculus and so on. People started being able to systematically express themselves mathematically, and one saw the kind of the rise of the mathematical sciences and so on. In a sense, what we're trying to do with our computational language is to do the same kind of thing, but now for the computational paradigm, to provide kind of a sort of full-scale language in which you can express things about the world computationally, and be able to both, as for us as humans, kind of crispen up our thoughts, but also to get a computer to help you and actually do things computationally and make use of all the sort of power that exists in the computational universe. So in a sense that, a large part of my life has been building that kind of bridge between what we humans think about and what's possible in the computational universe, and also sort of pulling in the kind of computational knowledge that exists in our civilization that's kind of sort of defines the things that we care about, so to speak. Okay, well, anyway, so that's kind of an introduction to sort of how to think about this notion of computation. Well, let's talk about physics. Back when I used to do physics, back in the 1970s and so on, there were these paradigms for doing physics, things like quantum field theory, general relativity, and there was a lot to figure out within those paradigms. And I didn't really even actually think too hard about questions like, what's underneath those paradigms? But after I'd seen all these things about the computational universe, I got kind of more ambitious. I got to think, well, maybe underneath all of this complicated mathematical physics and so on that we know, maybe actually there's just a simple program underneath all of these things. And just like in the case of something like Rule 30, we have this tiny program and it does all these complicated things. Maybe that's how our universe works. So I started thinking about that, and back in the early 1990s, I kind of wondering, could this possibly be the way things are? And in particular, when you think about if there really is going to be a simple program that basically makes our whole universe, one thing that is sort of inevitable is that all the things that we know about our universe today, that there are 3 dimensions of space, that the muon electron mass ratio is 206 point whatever, all those facts don't fit in a tiny program. So all those facts have to be emergent from that program. There has to be some tiny program, and only when we look at its consequences do we see all these features of the universe as we know it today. And so in a sense, one of the questions is, so what might the sort of fundamental raw material of the universe be like? What might be underneath kind of the things like space and time that we know about today? And I had some kind of ideas about how that might work, and I figured out actually, by the end of the 90s, I had actually figured out a lot about how to use kind of things underneath space and time, and how to reproduce things like Einstein's general theory of relativity from that, and so on. And they were kind of one part of this big book about a new kind of science. Really, the thrust of that book was exploring the computational universe as a way to understand things in the world. And I saw physics as just being a particular use case. People, I think, physicists at the time were like, oh, no, we don't need a different way to do physics. We're good, but it didn't work out that way. It was, there's been sort of at different times in history, people are like, we're really close to having a fundamental theory of physics. But it didn't work out in the kind of traditional flow of quantum field theory and things like that. So, and for a long time, I had been kind of meaning to go back and kind of explore these ideas further. Didn't get around to it, and then about a year and a half ago, was it? A couple of young physicists interacted with me and said, "Look, you've really I had kind of a new idea that was sort of a technical advance in how to think about these kinds of things." But they were like, "This really is too important to like let another 50 years go by and nobody look at it. We got to work on this." Actually, one of them, Jonathan Gorard, I think, is on this live stream and may already be answering questions and explaining things to folks there. But okay, so the result of this is that we were able to really make a lot of progress in understanding fundamental theory of physics. So let me try and describe a little bit about what we figured out. So first question is, what's the universe made of? So first let me just show you, if you're interested in more details, there's this big website that has tons and tons of material on it. But there's kind of a visual summary on here, which is kind of the rough picture of sort of how we think the universe is built. So one question is sort of, what's the universe fundamentally made of? And so sort of a fundamental question there is, what is space? Well, that's not a question people usually ask. You know, ever since Euclid, it's just been, well, space is this thing that things exist in. You know, you can take a point, you can put the point anywhere you want. The point has no extent. It's infinitely small, and you don't have to say where it is. But actually, we don't think that's right. We think that actually space is not a continuous thing where you can just put the point wherever you want. Space is discrete. It's actually made of a bunch of discrete points. Now, in a sense, we've seen this story before. When we think about something like water, we might say, well, water is a continuous fluid. We might say, well, we can pick any point in the water and there's still water there. But it's not true, because actually water is made of a bunch of discrete molecules, and you either hit the water molecule or you don't. It's a discrete kind of thing. Well, we think space is like that too, that space is not continuous, which is what has been assumed in both physics, mathematical physics, and sort of it's a Euclid and after kind of assumption that space is somehow continuous. We don't think that's correct. We think instead that we should think of space as being made of kind of atoms of space, just as materials are made of atoms of materials. And those atoms of space are just points, disembodied points. How is space sort of put together? Well, we think that that space is a big network. And really all that's said is there's a point, and the point has certain neighbors in this network. The point is connected to other points. We might just say space is abstractly made of a bunch of elements, and these elements have relations that relate them to other elements. And that's what space is, in a sense, that it's just this giant network. It's actually formally a hypergraph. So an ordinary graph is something where every point, pairs of points are connected together. In a hypergraph, you can have more than 2 points connected by a hyperedge. But the basic idea is it's this giant hypergraph that contains many points. Like in our universe, there might be 10 to the 400 points, a very large number of points in our universe. And then just like water on a large scale seems continuous to us, so space on a large scale seems continuous to us. The microscopic atoms of space might be 10 to the minus 100 meters across. By comparison, like a proton is 10 to the minus 15 meters across. And so very, very tiny on that scale. But the idea is that space consists of this discrete hypergraph. And then the question is, okay, so if that's the case, there's sort of what happens is on a large scale limit, space seems continuous and three-dimensional. On a small scale, it might not be that way at all. And it also is not to be guaranteed that space is three-dimensional as opposed to 3.1 dimensional, as opposed to something else. All of those things are determined. There's no sense in which these points exist at coordinates in space. They just have a relationship to each other, and it's an emergent thing that there's a large-scale continuous structure to space. That's kind of the notion of what space is. By the way, I should say that there's a question of well, what exists in the universe? Normally in current sort of physics, we've thought of there's sort of a background of space, and then there's matter and energy and things that exists in space. In this model, it's very minimal. The only thing that exists in the universe is basically space. There's just this giant hypergraph, might have 10 to the 400 nodes in it, and everything that exists in the universe is a feature of this hypergraph. Now, that might seem bizarre, but it doesn't seem quite as bizarre when you start looking at something like, well, you know, for example, that, let's see if I can pull this up again, yeah, here's one, cellular automaton, where, you know, here, everything is just made of a bunch of discrete black and white cells, but yet there are these structures that emerge just as a feature of the dynamics of the system. And so it is, we think, with space in the universe, that there's just a discrete, just this discrete hypergraph, and features of that hypergraph represent all the things that exist in the universe, all the electrons and particles and energy and all those kinds of things. That's a little bit, in a sense, disappointing, because in a sense, when we work out how much of the activity of the universe is involved with the maintenance of the structure of space versus being involved with all the things we care about, all the electrons and protons and all those kinds of things, it seems like it's maybe about 1 part in 10 to the 120 is the stuff we care about. And the other, all the other parts in the 10 to the 120 are all just to do with the maintenance of the structure of space. Okay, so how does that's sort of the structure of space. How does space, what happens in space? You know, what is the progression of time? So in our way of thinking about things, time is a process of computation. What's happening as time progresses is that this hypergraph is being progressively rewritten. There are rules that say, for example, if you see a piece of hypergraph that looks like this, rewrite it to one that looks like that. And all the time, all over the universe, this is what's happening. There's this structure, this hypergraph that represents space, and that structure is being continuously rewritten. And that progressive rewriting is the progress of time. And that kind of, this particular model of sort of the irreducible progress of time, this phenomenon of computational irreducibility that I mentioned before, is something that is fundamental to the progression of time. That that also explains how thermodynamics works and a bunch of other things. That there's this kind of notion of computational progress is the progress of time. Well, so the first thing you might say is, okay, that's great, but how can that possibly be right? We've known since 1905 this idea of special relativity that kind of say that space and time are sort of the same kind of thing. How can you be saying that space is the extent of this spatial hypergraph and time is this progression of computation with time? Well, it's a little bit subtle, but here's how it works. So what happens is, when you are an observer embedded within this universe, so you're part of this hypergraph, there's a question of what can you actually tell about what's going on in the universe. And it turns out the only thing you can tell is about updating events and the relationship between updating events. In a sense, what you can see is every time one of these rules gets applied, it's like a little event that happens. It's a little thing that happens to this network. And you can ask the question, when you look at those different events that happen, what is their causal relationship? That is, an event may be not able to happen yet because the input that it needs has to come from the output to some other event. And so there's that defines kind of this partial ordering of events. that defines kind of this thread of causality, this kind of set of causal relationships. And from that, you build this kind of causal graph that represents the causal relationships between events. And it's, I mean, in a sense, a very extreme version of this. Imagine you're an observer in this universe, and imagine that in the universe, only one event is ever happening at a time. But where that event happens kind of runs around all over the universe. You might say that theory can't possibly be right. After all, I can see that things are happening elsewhere in the universe. But the point is, you don't get to see anything until that event has come to you, so to speak. So as that thing zips around, you're kind of frozen until you get updated. And you can't tell what's been updated until you're updated. And anyway, in the end, what you've realized is the only thing you can actually sense is this kind of causal network of the causal relationships between events. Well, it turns out there's another important phenomenon that we call causal invariance, which has the feature that you might say, well, I'm saying, I think I forgot to say one thing, which is when you do these updates, there may be many possible updates that you could do in this network. And the question is, which one do you do first? Which one do you do later? Well, it turns out that when there is this phenomenon of causal invariance, it simply doesn't matter in what order you do those updates. It doesn't matter to the causal graph that you get out. The graph of causal relationships is unaffected by the particular order in which you did those updates. It's something that is just dependent on the structure of the system. It's something that has this causal invariance property. Well, that causal invariance property and the fact that one's just dealing with this causal graph turns out to be the story that leads to special relativity. It turns out that the phenomenon of the idea that sort of physics is the same whether you're stationary or going at 1/3 the speed of light turns out to be just that those are just different ways to sample this causal graph, and you're sort of guaranteed to have the same causal graph because of causal invariance. And actually, you can go even further than that, and you can discover that when you look at the spatial hypergraph, you can start asking questions like, well, let me go into a little bit more detail here. You can start asking questions about the spatial hypergraph. Let's start looking at a few more details about how this works. So there's kind of a typical rule for the spatial hypergraph, and this is let's say we start off from that initial condition. We can just run it. It's a little bit like the cellular automaton. We're just running it, and even though the rule is very simple, the structure that we get out may be pretty complicated. And if we change the rule, we'll get out different kinds of structures. We can get all kinds of wild things happening. Now, just sometimes, here's a rule. It's another pretty simple rule. We run it. This particular case, we get out a structure that's rather simple. It's kind of knitting this kind of simple sort of fabric-like thing that looks to us just like a sort of a two-dimensional grid. And sometimes we can get, here's another one. This is another simple rule. This one creates a thing that looks like this. Now, when we're drawing these pictures, it's worth understanding that these are just ways of rendering this graph. The only thing we know for sure is how the points are connected. So this is the same graph, but just rendered in different ways. So that particular node will be connected to the same nodes, but here we're drawing it in different ways. So the question is, when we look at these graphs, and we imagine a very, very big one of these graphs, what is the effective dimension of this thing? In other words, if it was going to behave like a grid like this, what dimensional grid would it be? Would it be a one-dimensional thing, a two-dimensional thing, a three-dimensional thing? And how do we tell? Well, there's a pretty easy way to tell. Here's how it works. So let's say we have something which is a grid. We can readily say it looks like a two-dimensional grid. We start at some point in the grid. We just sort of grow this region, progressively bigger region. And we say, how many points are there? If we go r steps here, how many points do we get to? Well, here it's r squared. It's making just a square. If we go to the version in another graph that happens to be drawable as a three-dimensional grid, then we do the same computation, the same way we look at the growth of this kind of region. It will grow like r cubed, and that cube, that third power, is the thing that tells us the effective dimension of this network. Well, we can do the exact same thing for one of these systems that we're growing from our underlying hypergraph rules, and we can work out, what is its effective dimension. There's just a plot that shows how to work that out. And in that particular case, the effective dimension is about 2.6. So for any one of these kind of, for many, not all, for many of these kind of hypergraphs and so on, there is a limiting dimension. There is some definite value of the effective dimension of the thing when viewed as something which is sort of a large-scale continuum thing. Well, it turns out not only is there a dimension, there can also be a curvature. So in this particular case, we say, well, that's roughly a two-dimensional grid, but it looks like it's curved. Well, you can work out curvature in kind of the same way that you work out dimension. You just say, we start from a particular small region and we start growing it, and we say, what's the area of that region? So, the area of a circle, pi r squared. But if you draw a circle on a sphere, its area isn't exactly pi r squared. It's pi r squared with a correction that depends on the curvature of the sphere. And you can do exactly the same thing with these hypergraphs. And from that, you can work out the effective curvature of the effective continuum space that corresponds to the limit of this hypergraph. Okay, why is that significant? Well, it's significant because the whole idea of Einstein's general theory of relativity is this idea that space can be curved. The idea is, light always travels in what it thinks are straight lines. You shine a laser, it's going to go in a straight line. The question is, what's a straight line? Because on a plane, straight lines are ordinary straight lines, but on a sphere, on a curved space, straight lines aren't straight when you look at them from outside. And what's happening in Einstein's theory of gravity, the basic idea is the presence of mass and energy causes curvature in space. And then what counts as a straight line is deflected by the fact that there's curvature in space, and it's that deflection that is responsible for the change in motion that's associated with gravity. Okay, so in our models, we get the exact same thing happening. We get that the limit of these hypergraphs has curvature, and we can work out, it turns out, it's a big clue very quickly that I knew from a long time ago, that the correction term is proportional to a thing called the Ricci scalar curvature, which is exactly the thing that occurs in Einstein's equations. So what we discover in the end is that the large-scale limit of our of the behavior of our network behaves just like physical space according to Einstein's equations, according to Einstein's general theory of relativity. In a sense, it's analogous to the following thing. If we look at a fluid like water, we got a bunch of molecules bouncing around, and we can say, what are the continuum equations which are satisfied by the continuous fluid, thought about in terms of velocities and things like that, rather than in terms of individual molecules? That same kind of derivation we can now do for space. We're making space out of atoms of space, and we're looking at what is the continuum equations that arise from that. And the continuum equations, very cool fact, end up being exactly Einstein's equations. Now, the way Einstein's equations are set up, there's sort of two pieces. One is the vacuum Einstein equations, what happens when there's no matter around, and the other is the Einstein's equations in the presence of matter. And did I put my window here? The question is, how do we figure out? I said that matter is just a feature of this spatial hypergraph, but one of the things that's important about matter is energy. And it turns out, somewhat to my surprise, that there ends up being kind of a bulk way to understand what energy is in our models. Energy is basically the amount of activity in the network. And so you can think of that as, in this causal graph, there are these kind of causal edges that represent the fact that one event happened and it affects another event. Well, that, if we look at the flux of causal edges sort of through what are called in relativity theory space-like hypersurfaces, that is kind of the constant time surfaces. If we look at sort of how much activity is happening through time, that amount of activity, flux of causal edges through space-like hypersurfaces, more formally, is precisely energy density in our models. So in a sense, a feature of the causal graph gives us energy. A feature of the causal graph, the flux sort of sideways through time-like hypersurfaces, gives one momentum. And it's very kind of nice. One can quite easily derive E equals mc squared from this, which is something we haven't been able to derive before. It's just been a fact of nature before. We can derive that from properties of these causal graphs and so on. Well, so when we have this idea of energy associated with these causal edges, that it turns out that the way that energy enters there gives us precisely the full version of Einstein's equations. Let me explain one piece of this. So one of the things that's important in thinking about space-time is this idea of JD6, shortest paths, the kind of what a straight line is, even though space may be curved, so the line may not really be straight. So this notion of JD6 are what particles which aren't acted on by forces other than the forces associated with the curvature of space, gravity, they're the paths that they follow. So the question is, what do JD6 do in our models? Well, it turns out that JD6 are deflected by the presence of causal edges. And that's something you can it's not super hard to see that has to be the case. But it turns out that the amount of, so when there is energy present, there are causal edges. When there are causal edges present, there is a deflection in JD6. And that deflection in JD6 is precisely the deflection that's associated with the force of gravity. So cool fact is that one can then derive general relativity from these models. So we started off just from the sort of atoms of space and this kind of general idea of these rewrite rules and so on, and we can derive general relativity. We can derive features like black holes and so on. You can actually see what, when you look at a causal graph, this is a sort of a typical causal graph. Here's a causal graph that has an event horizon. So a causal graph, every one of these yellow dots is an event. And these edges say this event affects this event, which affects this event, which affects this event, and so on. But if you're over here with events over here, these events here can never affect these events here. And that's what happens when an event horizon forms. This is effectively like a black hole. Actually, this particular one is more like a cosmological event horizon. But it's a place where some part of the universe can no longer have a causal effect on another part of the universe. And that's another thing you see in these models. And by the way, the thing I looked at recently was a question about faster than light travel in these models. And it turns out that I can answer questions about this. It turns out that the problem of faster than light travel becomes a problem that is more like a generalized engineering problem than a physics problem. It's kind of like being able to do faster than light travel is like asking for all the gas molecules in a room to all assemble themselves. And let's say for one gas molecule in a room to just find exactly the right way to jump off other gas molecules to be able to go really fast to the other side of the room. That ends up being sort of the problem of faster than light travel. And it's something which, in principle, when you look at things in terms of these kinds of models, in principle is possible. Although it may be as in practice as impossible as it is to get that one molecule that manages to sort of do enough computation to see where to go, manages to sort of beat computational irreducibility to do that. All right, let me not go off too much in that direction. Let me go back to talking about sort of the overall story of physics here. Okay, so one big piece of physics is the idea is gravity and the large-scale structure of space-time. Another big piece of physics is quantum mechanics and small-scale structure of space and small-scale structure of the universe. So in classical physics, what we end up with is models that say definite things are going to happen. You know, you throw a ball, it follows a particular trajectory. The big idea of quantum mechanics from 100 years ago is, no, actually, definite things don't happen. Rather, all possible paths are followed, and we just get to know certain probabilities for outcomes. So in a sense, there isn't a deterministic trajectory for the ball. It's like it breaks into all possible paths, and we just get to see certain probabilities. Okay, so how does that work in our models? Well, what's really interesting is that quantum mechanics is not something that you sort of insert into our models. It's something you cannot avoid in our models. It's inevitable in our models. And the reason is this. I talked about doing these updates. Problem is, you do these updates wherever you can, but there are many possible paths for doing these updates. There are many different ways these updates could get done. There isn't just one unique way the updates could get done. And so what you end up with is what we call a multi-way system, where you start off from this initial condition here. Then in this particular case, there was only one way the update could get done. But here, there were three ways it could get done. And you end up with three different, essentially, configurations of the spatial hypergraph associated with these three different ways that updates could get done. And down here, you get more. And one thing that's interesting is not only do you get these branching events where two different things can happen, you also get merging events where a different sequence of of possible updates could end you up at the same state after a few steps. Okay, so it turns out this branching in this multi-way graph seems to be the story of quantum mechanics. This seems to actually give one quantum mechanics. And what's happening here is essentially the different possible paths that you follow here correspond to different possible sort of quantum possibilities. The way of representing the quantum mechanics that is sort of the most effective way of doing it is through this thing called the Feynman path integral, where the idea is that you are defining all these possible paths and each one is given a certain weighting. Well, so what happens is that's what's happening here. And when we, let's see how to explain this. So one of the critical things, let's go back to space-time. When we observe space-time, we do it by picking a certain reference frame. We're picking a particular way that we define what counts as what's at the current moment in time. Where is simultaneity in time? Well, we have to do the same thing instead of observing quantum mechanics. We have to pick what we call quantum observation frames, which are kind of the direct analog of, and in a sense, those quantum observation frames correspond to different measurements we can do on quantum systems. And one of the things about quantum mechanics has been very hard to understand is why is it when quantum mechanics has all these possibilities going on, why is it that people think definite things happen? Well, in our model, what happens is these different quantum observation frames that correspond to different, essentially, choices of how to do measurements, because of this phenomenon of causal invariance, they all, in a sense, come to the same conclusions. It's the same reason that relativity works, is the reason that we have objective reality in quantum mechanics. Well, there's even another thing, which is if we look at this multi-way graph and we say, let's go back to this causal graph here. If we look at this causal graph and we say, this is going down with time, and we say, let's make a slice at a particular time, and let's see what we conclude about the universe based on what's happening at that particular time, looking locally at this causal graph. When we take that slice, what we will effectively get by analyzing that causal graph is we'll essentially reconstruct the spatial hypergraph that represents the instantaneous structure of space. Do the same thing in the multi-way graph. What do we get? We get this thing we call a Bronchial graph. So this Bronchial graph is a representation of essentially what the structure of branches in the system, the structure of what was related to what by having had a common ancestor in this set of branchings. So in a sense, in the world of quantum mechanics, this is a map of quantum entanglements. These different nodes here in this Bronchial graph are different quantum states, and these connections are representing sort of the closeness and entanglement space of those different quantum states. It's just like in the spatial hypergraph, following these connections in the spatial hypergraph tells us of the closeness of points in space. This is telling us the closeness of points in Bronchial space, in the space of quantum states. Okay, so why is this interesting? Well, one of the things that one wants to do is one wants to figure out in quantum mechanics, there are definite equations. They say, for example, in the path integral, there's an equation that says that the weighting of different paths is given by e to the I times s, the thing called the action, divided by h bar. Okay, well, so what we can look at is in this multi-way graph, we can ask, just like we asked about geodesics in space-time, we can ask about geodesics in the multi-way graph, and we can ask about the deflection of geodesics in the multi-way graph. And it turns out, and again, I'm compressing just a huge amount of physics and sort of abstract stuff here, and I'm just kind of giving you a sketch of what goes on. But basically, this idea of energy being flux of causal edges, that works also in the multi-way graph. There's a notion of a multi-way causal graph, and there's a notion of kind of a quantum mechanical analog of energy. What happens is the deflection of geodesics in the multi-way graph is determined by the presence of energy in this multi-way causal graph. And the deflection of geodesics, basically in physical space, the deflection of geodesics means your particle went somewhere different in physical space. In this multi-way graph, the deflection of geodesics says you're going somewhere different in Bronchial space. Okay, so it turns out that, again, in quantum mechanics, one of the big sort of mysterious things is the presence of complex numbers in describing sort of the amplitudes for different things to happen in quantum mechanics. I actually think that the sort of packaging of that as sort of a single complex number rather than the magnitude and the phase being separate is kind of a mistake that's been made. But in any case, the basic point is the phase of that complex number turns out to be essentially position in Bronchial space. And so the picture that we have here is the presence of energy is deflecting JD6 and causing them to end up in different places in Bronchial space. And that deflection process is what that sort of ending up in different places in Bronchial space is changing the phase of a quantum amplitude, which turns out to be exactly what the path integral, the Feynman path integral, says quantum mechanics should do. That S, that action is actually basically an energy density. And this is basically saying the presence of energy density deflects JD6, but not in physical space, instead in Bronchial space, and that shows up in the phase of these quantum amplitudes. And so this is, for me, one of the most sort of spectacular things here is that what this is saying is the thing that leads to the Einstein equations in physical space, the presence of energy causes deflection of JD6, that leads to Einstein's equations in physical space. The exact same phenomenon operating in Bronchial space leads to the Feynman path integral. So in other words, these two sort of threads of 20th century physics, general relativity and quantum field theory, they're actually the same theory, just played out in different spaces. And it's been a big mystery for a long time how those theories fit together. They're basically the same theory. And what happens is, for example, when you're looking at black holes and you're looking at quantum mechanics and its relationship to black holes, you kind of see the interplay between what's happening in space and what's happening in physical space and what's happening in Bronchial space. We don't understand all the details of how that works, but it's a lot of the things which have been very hard to understand and very paradoxical start to seem very natural in this framework. So, okay, well, that was a sort of a sketch. I don't know how I'm doing on time, horribly, actually. Okay, I should, that was sort of a sketch of kind of how this theory of physics works. I could go into lots more detail about how we understand particular phenomena in physics. Let me sort of end by talking a little bit about what do we learn from the fact that this seems to be how the universe works, and we can go into more detail about how we understand different phenomena in physics from this model. But it's going really, really well. I mean, we're progressively looking at different phenomena in general relativity and quantum mechanics and so on, and understanding how those things work. We're gradually understanding all sorts of kinds of experiments that one could do that would probe aspects of the universe that we haven't, in many cases, thought to look at before, that are informed by these models, actually working out, the deflection of light in this situation should be 1.7 times that. That's a lot of hard work, and we haven't got to that point yet. We're more at the point of saying these are kinds of things you should look at, like dimension change in the universe. Like in the early universe, maybe the universe started infinite dimensional and gradually cooled down to the point where it's three-dimensional, but maybe there are signs of dimension change that still exist that are detectable in the current universe and so on. But, things like that. But in any case, let me talk a little bit about sort of the bigger picture of what it means that kind of it's computation all the way down, so to speak. I think one thing to understand is I mentioned computational irreducibility, and I mentioned the phenomenon that let's see, where is this? I mentioned this phenomenon that when you run a system, you may not be able to predict quickly what it's going to do. You may just have to follow each step and see what happens. Well, obviously, that could be a real killer for a theory of physics, because it could be the case that, yes, we got the right theory, we got the right rewrite rules for our hypergraph, but running it for 10 to the 100 steps to find out what happens after 14 billion years is undoable. We might be able to work out what would happen in the first 10 to the minus 100 seconds, but we wouldn't be able to get any further. We'd be kind of stuck by computational irreducibility. And actually, I thought that was what was going to happen. I thought we were going to be able to say, yes, we've got a really good theory for the first 10 to the minus 100 seconds of the universe, but that's as far as we can go. But we didn't count on basically the achievements of 20th century physics. And what we came to realize is that whenever there's computational irreducibility, there are always pockets of computational reducibility. There are always some things you can say. And what happens in this case is those pockets of computational reducibility are precisely 20th century physics. There are two big kinds of things one can say, one about general relativity, one about quantum field theory, and they both manage to slide through kind of this general irreducibility. So it's as if underneath, when you look at all the details, it's all irreducible and there's nothing one can say. Just like you look at some water, underneath all the molecules are bouncing around in very complicated ways, but nevertheless, we can say that the overall flow works in this or that way. In a sense, it's sort of inevitable this has to be the case because we know that there are things about the universe that are predictable. We expect from the principle of computational equivalence that there will be computational irreducibility. But yet, in a sense, the way that we operate in the universe has to be such that we're kind of keying into those aspects of those slices of computational reducibility so that we can actually make predictions about what's going to happen in the universe and sort of lead our lives, so to speak. In a sense, computational irreducibility is what kind of makes it interesting because, you know, if everything was computationally reducible, we'd be able to say, well, I live my life, but I already know the answer is 42. I don't need to go through all these steps of living my life. I already know the answer. Computational irreducibility tells you that actually, no, that's not the way things work. There's sort of an inexorable thing that's achieved by the passage of time. It's this irreducible computation that's achieved by the passage of time. So in a sense, what we're seeing, 20th century physics represents the pockets of computational reducibility in this kind of bed of computational irreducibility. So then the question is, sort of a big question is, okay, let's say we find a rule, and we haven't found one yet, that reproduces all known features of physics. We found rules that reproduce, when any particular rule reproduces certain features of physics, we haven't found a single rule that together does all the things it needs, you know, finite dimensional space, particles, et cetera, et cetera, et cetera. We don't have a single rule that does all those things. We know that within this class of rules, there are ones that do all those things, but we don't have a single one that does all those things at the same time. But let's say we had that rule. We could just say, here it is. I can show it to you. You know, let me present it to you. Here's the thing. I can write it down in a small space. There's this tiny program, and it makes our whole universe. Okay, then isn't that really surprising? Because why should we have been the lucky ones who got that very simple to describe universe? Why, you know, in a sense, that was sort of the story of Copernicus was, you know, before 500 years ago, we were like, the Earth is the center of the universe, life, you know, we're unique. There's nothing, you know, and then the sort of the big realization, which came from a lot of science, was no, we're not unique. We're just, you know, this random planet on the, you know, the edge of some galaxy, et cetera, et cetera, et cetera. There's nothing special about us. So if we find the fundamental theory of physics and it's this little tiny rule, it's like, how come we got the little tiny rule? We didn't get the incredibly complicated rule. How come we got this particular one? So I thought we weren't going to be able to say very much about that question, but I was wrong. Turns out that there's a notion, just like I talked about this multi-way graph that represents following all the different possible updates that can be done according to a particular rule. There's a kind of what we call a rulial multi-way graph, which goes even one step more general. It says not only at every step can you can you do the particular ways that you do, can you make different choices about where you apply the rule, you can also apply different rules. And so this giant rulial multi-way graph, you say, how on earth could you say anything about this rulial multi-way graph? Well, it turns out it has causal invariance. And that means that when you put down a reference frame in this rulial multi-way graph, all reference frames, in a sense, give the same predictions. In a sense, what it's saying is there are lots of different ways that you can describe the universe, but within those description languages, it's always the same universe, just described in different ways. So just as reference frames in relativity correspond to different states of motion, reference frames in quantum mechanics correspond to different choices of measurements, reference frames in this rulial space correspond to different choices of kind of the overall description language that you use to describe the universe. So, you know, since I've spent a lot of my life as a computational language designer, this is kind of a fun conclusion for me, because in a sense, what it's saying is what's going on is we have to come up. Our project of finding a fundamental theory of physics is essentially a language design project. It's saying, find a description language which is useful to us, which we can implement on our computers, and which represents the universe. And there isn't just one of them. There might be many different ones, but some of those description languages might be completely unsuitable for us humans. We have particular senses. We are used to the idea, we are a particular size in the universe. So we, at the size we're at, we look around us. The speed of light is very fast compared to our brain processing speed. We think of things happening at slices, moments in time, that things happen throughout space at moments in time. If we were much bigger, if we were kind of planetary scale, the speed of light would make us not conclude that things like that were happening. So it's the description language that we have for the universe is very much keyed into who we are, so to speak. And one of the things that one realizes is there actually is an infinite collection of different description languages that you could use for the universe, which are utterly incoherent from each other. So our one is the one that sort of works given our senses, given our sort of experience of the world. But we could have a completely different one. And I was used to think, if there are extraterrestrial intelligences, at least we share the same physics with them. But it isn't true. It's we can expect that there can be these sort of utterly incoherent views of how the universe is set up based on these kind of different description languages for describing things. But the really remarkable thing is that even with all of that sort of floppiness, we can make definite conclusions. And it looks like there's a very beautiful way in which some sort of very abstract ideas in mathematics that involve things like higher category theory and so on, that these sort of converge with these ideas about physics. And it's possible to understand kind of one of the things that we've been interested in is how the kind of meta-mathematics, the theory of all possible mathematics, is kind of converges with the way the physical world works. But these are kind of things that sort of emerge from this computational view. All right, I should wrap up here, but I think the main story here is in the last 45 years, big thing that's happened is this kind of idea of computation, about thinking about things in computational terms, thinking about programs as descriptions for things, both thinking about sort of the world at a practical level in terms of computational language, having this computational language to describe the world, to go from human thoughts to things that can be implemented computationally, in a sense, using that computational language to sort of enable computational X for all fields X. But then in particular, for physics, using this idea of computation to try and see how do we sort of drill down, how do we find out what's the machine code on top of which all the physics that we know and our universe operates. And I think the thing that for me is super exciting and very unexpected, actually, is that we're really at the point where I think we know basically what that machine code looks like. We don't know all the details of the instruction set, but we know what the basic structure of that machine code is. And we can see how all these different things that have seemed like they're very beautiful, but very incoherent in physics fit together. And it's one of the things that's been exciting is there have been a bunch of approaches to mathematical physics that have arisen, particularly in the last few decades, that are very beautiful mathematically, but don't necessarily attach to the way that physics has seemed to be done. And what I think our models have provided is kind of a Rosetta Stone that lets one understand how all these different very beautiful pieces of mathematical physics, how they relate to each other, and how also they relate to at least being idealizations of the kinds of things that happen in fundamental physics. All right, I should wrap up there. So thanks very much, and I'm happy to try and have questions, discussion as long as we can go. Thank you.